Welcome back, everybody. Let's work through this group work on double integrals and maxes and mins. This first problem has us computing a double integral of our green function right here. There's our f over a triangular region in both orders, and we're going to pick one and compute it eventually. Let's start. Let's get a picture going. So our triangle starts at 0, 0, goes up to 1, 2, then over to 0, 3. And so we have this picture going on, and there's our triangle. So to set up the integral in the order dy dx, where we set x, move y, we are doing vertical cuts. So we are setting different x's and cutting vertically through this thing. And we can see that we're always moving y from this bottom line to this top line. So we just need equations for those lines. This middle point is happening at 2. And so this bottom side here has equation y equals 2x. This top side has equation y equals 3 minus x. And so we can set up our integral. Function dy dx. We're always moving y from our bottom side 2x up to our top side 3 minus x. And what x's are we doing this for? The x is from 0 to 1. In our second order, I'll just copy paste this same triangle, but now our cuts are going different directions. So now we are setting y and moving x, so we're imagining setting different y's, and where our cuts are horizontal. And so here we have something different going on. Below y equals 2, we're starting x at 0 and moving it to our line over here. But up above, we're starting x at 0 still, but we're stopping it at this other line. And so we'll need to use two integrals in this order. We'll want to solve our equations for x. So at the bottom, from y equals 2x, we get that x is y over 2. And up here, since y equals 3 minus x, if we add x and subtract y, we get x is 3 minus y. And so these will give us our start and stop instructions for x on both of these chunks of our region. So, setting this up, we have our two integrals. I'll just toss this down real quick. And for our bottom chunk, we're always moving x from x equals 0 out to that bottom line, y over 2. And the y's that we're doing this for are 0 up to 2. And for our top side of our region, we're always moving x from 0 out to the top line, 3 minus y. And we're doing that for y's from 2 up to 3. And so to compute this, let's definitely choose the top order, as we just have one integral, and we'll work through that. So just copy paste. Integral from x equals 0 up to 1, y from 2x to 3 minus x, of our function 2xy. So with our inside integral, y is our variable, x is a constant. And so with our variable y, the 2x is a constant. And so we're just going to get y squared over 2. And so this will become just x times y squared as our antiderivative. And we'll evaluate that from y equals 2x up to 3 minus x. And if we plug 3 minus x in for y, and then subtract what we get when we plug in 2x for y. We get the following: x times 3 minus x squared minus x times 2x squared. And if we work this out, x times 9 minus 6x plus x squared minus x times 4x squared, and we distribute that 9x minus 6x squared plus x cubed minus 4x cubed. And if we simplify this a little bit, just combining those two terms there, maybe I'll put that out front, we get negative 3x cubed minus 6x squared plus 9x. And we are integrating this from x equals 0 to 1. All right, that was just our first integration there. And notice that y is no longer involved, as it should be. And so now we just have one more integral to compute. And let's see if I can do this without moving the screen. So what are we going to get? So negative 3/4 x to the 4th minus 2, because we got x cubed over 3, x cubed plus 9/2 x squared, evaluated from 0 to 1. If we plug in 1, we're just going to get those coefficients added up. And then plugging in 0 just kills everything in there. And at the end of the day, we get 7/4. All right, let's look at our next one. So here we have a double integral that's fully set up, but we are told is not so great to integrate in this order. If you ask Wolfram Alpha or something to anti-differentiate it, it's a total disaster. And so in order to integrate this, our thought is, well, if we were integrating with respect to x first, things would be great. And so let's switch the order. But in order to do that, we can't just flop the two integrals. We need to draw a picture. We need to draw the region, then figure out our cuts in the new direction, and get our new start-stop instructions. And so here we have to read off our starting instructions from this integral, and our inside integral is with respect to y. And so we are setting x and moving y from root x to 2, and we're doing that for x's from 0 up to 4. And so we can get a picture going. So here is our root x function. And we're moving y from root x up to 2. So here's y equals 2. And we're always moving y from root x up to 2, from root x up to 2, from root x up to 2. And so this is the region that we are actually integrating over with our integral. But of course, we want to switch our order, and instead of setting x moving y, we want to set y and move x. So take our horizontal cuts like this. And notice we're always starting x at 0 over on this left side, and we're always stopping x over on this right side coming from our square root function, which solving this for x gives us y squared. And so here we're going to be able to set this up just with a single integral in our new direction and work from there. All right, so writing this out, if we're setting y moving x, we're always moving x from x equals 0 on the left over to our parabola, which is x equals y squared. And what y's are we doing this for? Y's from 0 at the bottom up to 2 at the top. Now, our inside integral, thinking of x as our variable, our entire function is just a constant, and so the antiderivative just gets an x multiplied in there. So we get x over y cubed plus 1 evaluated from x equals 0 to y squared. And so that gives us, let me maybe just move it over here, plugging in y squared for x, then subtract what we get when we plug in 0 for x. We get y squared over y cubed plus 1, and then when we plug in 0 for x, it just zeroes out. And so this is our function that we are now needing to integrate from y equals 0 up to 2, and we can just ignore that. So there's our dy. At this point, our x's have disappeared, as they should, and we're left with a single integral involving y. And although it looks like I have a 3 upstairs, it's really a 2, which makes this computable using u sub. Right? If we take our bottom function as our u, we can work this out. We can also do this kind of by hand, noticing that the derivative is up top, so we're going to have an antiderivative that involves natural log. To do this fully with a u sub, it looks something like this. Let u be y cubed plus 1, then du is 3y squared dy, and we see a y squared dy up there, so we'll toss the 3 over to the other side. And then our old limits get plugged into our u function, so 0 becomes 0 plus 1, which is 1, and 2 becomes 2 cubed plus 1, which is 9. And translating our integral here in terms of our u substitution, we get a new integral from u equals 1 to 9 of the y squared dy just becomes 1/3 du, so I'll toss the 1/3 out front, and then our fraction here just becomes 1 over u, which has the clean integral of natural log. So this is 1/3 natural log. Technically, we should include absolute values there, evaluated from u equals 1 up to 9. We get 1/3 natural log of 9 minus 1/3 natural log of 1, which of course disappears, and we're left with our final answer. Last problem is a min-max problem where we are looking for the absolute min and maxes of our function here on a triangular region. And from the extreme value theorem, there's 2 possibilities where these things could be hiding, either at a natural critical point of our function or along the boundary at a min or max along there. So to start, let's get a picture of our domain we're integrating over, not integrating, sorry, min-maxing over. So vertices 2, 0, and 0 plus or minus 2. Whoop. Perfect line. Nailed it. Here's our triangular region we're integrating and min-maxing over. And so to start, find the critical point of our function up here. So we want to take the 2 partials and see where those are both 0. All right, so partial with respect to x gives us 2x minus 2, and with respect to y gives us 2y. So if we set these equal to 0, this first one happens add 2 divided by 2 when x equals 1, and the second one happens when y equals 0. And so in our heads, how we can interpret this is that where the points where fx are 0, those are all the points with x equals 1. All right, so those are where fx equals 0. Where fy equals 0, it's all along y equals 0. Those are all the points where fy is 0. And so we're looking for the points that are both blue and pink, and there's one right there at 1, 0, which happens to be inside of our triangular region. So right there at 1, 0, we have a critical point of our function, and so we can grab the function value there just by plugging it in. We'll get 1 squared plus 0 minus 0, so I guess that is 1. Now we need to look around our boundary and find the values there, and I'm realizing I just misspoke. Sorry. If we plug this into our function, we will get f at 1, 0 is 1 squared plus 0 squared minus 2 times 1, sorry, which is negative 1. So if you're like, hold on a minute, good catch. Okay, now we're good. Now we can look at our boundary. Maybe the cleanest one to start with is over here on the left. That's where x equals 0. So if we plug that into our function, we get f of 0y, and we're going to get 0 plus y squared minus 0, which is just y squared. And in general, we would want to see, well, along x equals 0 from these y values, right, using y from -2 up to 2, where is this y squared function biggest and smallest? In general, this could be either at the endpoints or at a critical point. Right, this is just a Calc 1 min-max problem. But y squared is clean enough where we can just eyeball it, right, from -2 to 2. This is going to be looking like just our favorite parabola. And so it's going to have its minimum at 0. The minimum value is 0, and the maximum value is 2 squared at both those endpoints. And so here we can record that on our diagram over here on the left. So our function value is 0 at the middle and 4 the top and bottom. So that's our first side over on the left taken care of. Over on this bottom side, we need the equation, and it's y equals x minus 2. And so that's what we are going to plug in and use the x values from 0 on the left up to 2. So if we feed that in, we get x squared plus x minus 2 squared minus 2x, which, doing a little bit of algebra here, x squared plus x squared minus 4x plus 4 minus 2x, which is 2x squared minus 6x plus 4. And this thing could be either minned or maxed at a critical point or on a boundary point, and that could be either at x equals 0, we already know what's happening there, or here at x equals 2, which is a new point for us. And so we should plug that in. So maybe at x equals 2, see what we get, and our function value there, which maybe we can do in green, is going to be 2 times 4 minus 6 times 2 plus 4, which is 8 plus 4 minus 12, so that gives us 0. For our function value there. Just do a quick sanity check. If we plug 2, 0 into our original function up here, we do get 4 plus 0 minus 4, which is 0. Great. So next, we have our critical points coming from where our derivative is 0, and so the derivative here is 4x minus 6, and if we set that equal to 0, we get 4x equals 6, which then we divide by 4, we get 3/2. And if we plug that into our calculator, we get -1/2. So if we plug that into our function value is -1/2 there. And so this is coming from our purple line at the x value 1.5, which is closer over here. So f equals -1/2. Now, we technically should look at this top side as well, which has equation -x plus 2. But I claim that when we plug that in to our function, -x plus 2, which is x squared plus -x plus 2 squared minus 2x, because of the square, we're going to end up with exactly what we had before. So we have a mirror image. And once again, our kind of critical point of interest is going to be over 1.5 and give us a function value of -1/2 there. And with that, we have all the possible points where our absolute min or max could be hiding. We just have to look for the biggest and smallest. Looks like the biggest are on the left-hand corners of our triangle, and the smallest is -1 happening in the middle here. So here we have our absolute maximum values of 4 happening at -0, -2, and 0, 2. An absolute min value of -1 happening at the point 1, 0.